In this video, we're going to have an introduction to the properties of alkenes. So we saw that in earlier chapters, alkanes with ane at the end are going to be C single bond C, things with single bonded carbons, whereas alkenes, as we'll see in this chapter, are going to be things with double bonded C, double bonded to C. The naming will track as such. We have ANE denoting alkanes, ENE denoting alkenes. So for instance, if we have H3C, CH3, we would name this ethane. If we had H2C double bonded to CH2, we would name this ethene with an ENE. Naming is similar to the naming of alcohols. The priority goes to the double bond unless there's an alcohol in the molecule, in which case the priority would go to the alcohol. So for instance, if we have this molecule here with a double bond here, we have two options of naming it. We can name it from right to left or left to right. In this case, we want the starting position of the double bonds to be the lowest number. So we would start from the right and go right to left. So we number it this way. So we go 1, 2, 3, 4, 5. And the way we would number this is we'd have 2, and then we'd have the base chain, pent. It's a 5-carbon chain, so we have pent, and then we'd end with ENE to denote that's an alkene. Another way to be more specific that the 2 is for the double bond, the 2 is for the alkene. We could name this as pent 2-ene. And we'll see that with other substituents like alcohols that have endings, we will have to add the 2 as an interior number to the pentene, just to denote what falls where. Just to add substituents, if for instance we had not that 2-pentene, but we had this bromo substituted 2-pentene, again we want the first carbon in the double bond to be the lowest priority substituent. So we're going to number right to left. We go 1, 2, 3, 4, 5. We see that our bromo falls on the 3 position. So we have 3 bromo, and then 2-pentene. And again, we can do the same naming as such over here. We could do this 3 bromo pent 2-ene to denote that the 2 position is where the alkene starts. Now, what I was saying is if instead we start with an alcohol, say we have this compound here, we've added an alcohol to the end. The alcohol will take priority over the alkene. So instead of numbering right to left, we're going to number left to right in this case. We want the alcohol to be the lowest priority substituent. So we'd have 1, 2, 3, 4, 5. We have a 1 alcohol, we have a 3 bromo, and we have a 3 alkene. So we'd start with our 3 bromo. We'd have 3 bromo. And the way we number, since alcohol adds all to the end and alkene adds ene to the end, since alcohol has a priority substituent, we're going to end all to the end and put the ene in the middle. So what that looks like is we have 3 pentene and then 1 all. We could also label this as pent 3 ene 1 all, indicating that the 3 is for the alkene and the alcohol is on the 1 priority substituent, or 1 is the 1 position substituent, excuse me. Other ones to be familiar with are if we have a substituent that is right on a double bond, we call this vinyl. So for instance, if we had a chloro substituted group, we would call this vinyl chloride. Now, cycloalkenes are named similarly to cycloalkanes. So for instance, if we had this compound here, we'd want to put the lowest priority substituent as the double bond, and so we'd want the double bond to be the lowest, so we'd put 1 here, 1, 2, 3. And now notice if we could put 1 here at this position here, and so that our methyl would be 2, but we want the alkene to be adjacent numbers. If we put 1 here and numbered around, we would end up with 1, 5 alkene. In this case, we have a 1, 2 alkene, which is what we want. We want them to be consecutive numbers. So by doing it this way, our methyl falls at the 3 position, 4, 5. This is a cyclopentene. And the way we would number this is, or name this, is 3-methyl cyclopentene. You could put a 1 here to denote that the alkene falls at the 1 position, but in general, if it falls at the 1 position, you don't need to put a number on it. I'm going to draw one more example. I'll do it over here. Say we had a similar alkene, cycloalkene, and we had an alcohol. Just like numbering the linear alkenes, we want the alcohol to be the priority substituent, so we start here, 1, 2, we make our alkene number 2. If we went around in a clockwise fashion, our alkene would be number 4, which is less favorable than having it at number 2, 3, 4, 5. So how we would name this is we'd have 4-methyl 2-cyclopentene, indicating that the alkene falls at substituent at position number 2, and then 1-all. I'm sorry, that went off a little bit. 4-methyl 2-cyclopentene 1-all to indicate that the alcohol falls at position 1. Now, one thing to be careful of when we're naming alkenes is, as we saw in the previous chapter, chapter 3 and 4, is that alkenes can have stereochemistry about them. In fact, alkenes, the stereochemistry for alkenes deals with both cis and trans, and also E versus Z. So this is when you would want to review cis and trans, E and Z. So for instance, just to review cis and trans, we had these two alkenes. If we look, if we draw a line through the alkene, through the double bond, we see that these substituents are on opposite sides of one another, so we would call this trans. If we drew a line through this double bond, we see that the substituents are on the same side as each other, so we would call this cis. Trans and cis can only be used if you have two substituents on you have a disubstituted alkene, two substituents on the alkene. If you have more than two substituents, you need to move to the E or Z notation. So for instance, if we had this alkene, the bromo substituted alkene, we need to do the same thing as we did before in denoting whether this is E or Z. So we draw the line. We'd see that on this side, we have an implicit hydrogen here. We see that this is the priority substituent, and the bromo is this priority substituent. Since they are on the same side of the double bond, we would call this a Z alkene, and the way we would name this, we would have Z, 2-bromo, 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 2-butene, indicating that the bromo is at the 2 position and the alkene also starts at the 2 position. So the Z, the cis, trans, E or Z indicator will always go at the beginning. Sometimes you'll see it in italics. You can also put it in parentheses, and that'll all denote the stereochemistry of the double bond. If there's more than one double bond, you would put them all in parentheses, separated by a comma at the beginning of the name. Just to talk about alkenes, if we look at an alkene from a side-on view, I'll put on, so imagine that I have my substituents coming in and out of the plane of the board. We see that we have a sigma bond in between them. That's our single bond. And then our double bond is going to be our pi bond that forms when the p orbitals overlap on the adjacent carbons. So we have a sigma bond and a pi bond. This is what makes this a double bond. So this is a bond order of 2. We also see that these carbons here and here on the ends of the double bonds are sp2 hybridized, and we see that double bonds are a little bit stronger than single bonds. They're not quite twice as strong as single bonds because a pi bond is not the same strength as a sigma bond, but we do see that they are shorter and stronger bonds than their respective alkanes rather. Another thing we see is if we were to look at the geometry, we see that these 4 bonds here, 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 and here, as well as the carbons, are all in the plane. So this is a planar molecule. and then we have these pi orbitals sticking out of the plane above and below. And if we were to examine the bond angle, remember sp2 hybridized carbons or sp2 hybridized centers are going to have a bond angle of 120 degrees between the adjacent bonds. Now, alkenes have similar properties to alkanes. We see that C2 to C4 alkenes are going to be gases. That's ethene, propene, and butene. Above that, we get liquids, and eventually we get to solids, as we see with saturated fatty acids. Those are going to be solids. Unsubstituted alkenes are nonpolar, but substituted alkenes can have a dipole. So, for instance, if we look at this alkene, this is just ethene. This would be a nonpolar molecule. We represent the pole by the dipole moment by the letter mu, and that's given 0 debye. If we instead substitute one of those for a methyl, and we had the methyl substitute, so this is 1-propene, we would see that there is a dipole that actually forms right here. There's an electron density, as we see over here, there's electron density in the pi bond, so those make those a little bit more electronegative than an alkane substituent, so we'd have the dipole pointing towards the alkene, and we'd see that now we have a slight dipole of 0.3 debye. If we did an even more electronegative substituent, such as a chloride or chlorine, again, we draw the chloride is more electronegative than the carbon, so we have the dipole facing there. In this case, our dipole moment is 1.4 debye, so we're getting even stronger. What we see is if we combine both the methyl on one end and the chloride on the other end, dipole moments are additive. In vector math, they're going to be additive. So we have a 0.3 coming from the methyl, and we have a 1.4 coming from the chloride. These two would add together, so our overall dipole moment would be 1.7 debye. So we can get polar molecules. Substituted alkenes can be polar enough to dissolve in polar solvents, but for the most part, especially if we're looking at unsubstituted or hydrocarbon-like alkenes, they're going to be nonpolar molecules, only soluble in nonpolar solvents like hexanes or toluene. Alkene stability trends with a couple different things. It trends with both substitution and cis or trans isomerism. So what we see is we can have various substitutions on an alkene. We call this monosubstituted if it has one substitution. We have disubstituted. So that there's a couple isomers for disubstituted. So we can have that. We can have trans, and we can have cis. Oops, just one. So this would be disubstituted. We can have 3 substituents. This would be a trisubstituted alkene. And then we can have 4 substituents. And that would be called a tetrasubstituted alkene. So what we see in terms of stability is that tetrasubstituted alkenes are going to be more stable than tri, which are going to be more stable than di, which are going to be more stable than mono, which obviously are more stable than the unsubstituted alkenes. And this is because, as we've seen, alkyl groups are going to be donating electrons into the alkene, which is going to be more electronegative, a little bit electron deficient. So it will stabilize this CC double bond. The added bonus to this, or the added complication, is we also have cis and trans isomerism that can occur in disubstituted alkenes. What we see is if we look at the trans versus the cis disubstituted alkenes, we see that the trans is almost always going to be more stable than the cis alkene, and that's because if we have bulk, especially if we have bulk on the R and R prime groups, we end up getting steric clash, steric hindrance between these two groups, which would further destabilize this double bond by sterics. So this top one is electronics. donation into the double bond. Cis is more stable than trans in general because of steric clashing, especially if you have large substituents on the alkene itself. The final piece of this puzzle is talking about cycloalkenes. As we saw, some cycloalkanes are very unstable, and that tracks with cycloalkenes. For instance, if we have cyclopropene, we already saw that cyclopropane is very unstable, but cyclopropene is even more unstable. sp2 wants it to be 120 degrees. Geometry wants it to be 60 degrees, so this is very unstable. This bond is very, very unstable. And that similarly tracks for cyclobutene. It's sp2, which wants 120 degrees. Geometry wants that bond angle to be 90 degrees. So this is very unstable as well. What we see is once we hit cyclopentene and cyclohexene and further, is that these are going to be stable alkenes, and that's because the bond angles approach what the ideal bond angle would be. Now, we do have the question of whether this wants to be cis or trans. What we see is that from C3 to C11 alkenes, so cyclopropene included, we're going to want these to be cis CC double bonds. So that's what we see here. We have the cis CC double bond. We have the cis CC double bond. At C11, it could go cis and trans are equal. And then greater than C11, it's going to favor trans, and that's because we are now essentially a linear alkene, and we're going to do the sterics preferred trans alkenes. It's essentially a non-cyclic alkene at this point.